All right, everyone, so let's get started. So welcome back. So today we're going to cover joint probabilities for discrete distribution. So I was looking over the material for this week, and this material is so important as you get into like advanced machine learning. This sort of stuff's going to come up. I was talking to a friend of mine who teaches a very similar class this semester in biomedical engineering, and he was saying he's not covering this stuff in his class this semester. So I think this stuff is still important. We're kind of going to be reviewing probabilities with multiple things going on. We did this earlier in the semester, but now we're going to do it with random variables instead. So I think this material should generally be pretty straightforward given what you've already seen. We're doing it now instead of just with events with random variables instead. So we're gonna do this today, and then on Thursday we're gonna get a little bit into continuous random variables. So probably I'm also going to use this, week. There are a couple things that I wish I had covered earlier, which I didn't. So I'm going to try and squeeze those in at the start as well. And so before we get into the material for the lecture, a couple things I wanted to talk about. So homework 4 is officially out. I had printouts up here, but so everyone picked out all the printouts I had. This is due the first Tuesday after spring break. Typically not a huge fan of assigning lots of work over spring break, but we've covered all of the material that homework covers, so you should be able to complete it this week and then not have to do it over spring break. I know that's not how everyone works. You have midterms and other classes a lot this week. So if not, you can, you could do it over spring break, which would be fine. Or it's not due till Tuesday. And remember, there are a bunch of office hours on Monday and Tuesday of the week after spring break. We won't have office hours during spring break. I'll try and be around to answer questions on Canvas and stuff. But so you can get started on that. If you don't want to do it over spring break, you can do it afterwards. If you want to catch up on stuff over spring break, that's also good. The other thing I wanted to talk about was the quizzes. The first few quizzes, the scores were roughly where I was hoping they'd be with the class. In the average was in the 90s, and after that the averages dropped down to in the 80s, and it's kind of varied in the 80s. This is probably okay, but I'd like to have the averages on the quizzes be higher. So I don't plan on making the material significantly easier. I think it's at an okay level, but I would like everyone to do better on the quizzes. So I proposed, and I put this in an announcement on Canvas, that we would change a little bit the timing of the quizzes, and I would not open the quiz until after the lecture on Thursday. Then I would use the last 15 minutes of class on Thursday to review the material that we had that week. I think this would help everyone do better on the quiz. But then we wouldn't have a specific time in here that I would necessarily be totally sure I'd be around to answer questions. The fraction of, two things about this. One, the fraction of people who are sitting in here taking the whole time has been probably going down. There have been people on Zoom as well. But it's not a huge fraction of the class. And two, I feel like we've done a pretty good job of making the quizzes so fairly clear, and there haven't been a lot of like ambiguities. We've been kind of, so trying to work pretty hard on that. So I feel like this is overall going to be a good idea. You just have to start 15 minutes late. You don't get the class time to do it. So I just want to see if anyone has any concerns with this, or if anyone thinks this is like a really good idea. But I would give a chance for feedback before we enact it. Yeah. Great. Yes. Yeah, so I'll still plan to record it. So I would have an extra 15 minutes a week to actually review material. I feel like there's a little bit more material I'd like to cover every week, including a review that I haven't quite been able to get to as much as I'd so planned to in the lectures. Yeah. Yeah, so it'll still be open until the end of the day on Friday. So I'll still give you flexibility to take it. The point of the quizzes is to make sure you guys are not kind of delaying material until the midterm, or which we don't have. We're doing this instead, or until the end of the semester, or until the homework is due. I want you guys to be reviewing the material every week as it's coming out. And so that's why we have quizzes every week. All right, so, but the flexibility of it, I'm going to keep that. Yeah. Most of the time. So what I found out is there's an anatomy class which does not have lectures in here, but they have the exams in here 3 times a semester. There was one a couple weeks ago. There'll be one about 2/3 of the way through the semester, and then I think the last day of the semester. So there'll be a couple times we won't be able to be in here. So that's most times we will. Could probably go in the hallway. I think as soon as we're out of here, they will file in. I think it starts like 5:10 or something. So we would need to get out of here pretty quickly. But then I'd be happy to hang out in the hallway if you guys wanted to do that. So that should happen twice through the end of the semester. I don't exactly know the dates, but I'm guessing probably, hopefully the next one will fall on a Tuesday. But I'm guessing probably the 16th or the 23rd will be the next one, and then on the last day of class. Oh, that's a Tuesday, so that should also be fine. So probably Tuesdays, and we won't have a quiz that day. Yes, this sounds good. All right, so we'll plan on that starting this week. So we'll change when the quiz will open on this Thursday to be after class, and I'll get to do a small review after class. Yeah. The quiz due dates can be exactly the same, end of the day Friday. Yeah, so that will stay the same. Yeah. I don't care if you take it here at home, whichever suits you, in order to do that. Again, if you haven't been doing as well in the quizzes, some general tip I have that I recommend in a number of my other courses, I've required people make like a cheat sheet and then upload that to Canvas. It's kind of cumbersome to kind of check to do this, but doing this is a great way to kind of distill the information that we covered that week down. And then it gives you an easy reference during the quiz to look stuff up, and it should make the quizzes even faster to complete, because you don't have to dig through all the notes to find material if you don't remember everything offhand. So great. So sounds good. So let's plan on that. Okay. Yeah, well, I guess one thing on quiz 6, there are a couple questions about showing work. There was a little, it's hard to show up here. There was a little box where you could put an answer in or calculate an expected value. And if you just put in the answer, then like the autocorrect would, the auto grade would be able to tell you right away if it's correct, but you could put work in that box too if you wanted to. That was confusing for a couple people who emailed me, but most people seem to figure that out okay. That seemed a lot less cumbersome than having a big box down below. But it's so in case that comes up again in some future quizzes. Yeah. Yeah, so I'm kind of, you will find out soon after if you get it right. I think the TAs managed to grade them all by so like Saturday this week, so it didn't take too long. And I found some people didn't like to write in that box, and there was actually, I think, more people were writing down their answer offline and then trying to upload in that box, and because of that, they ran out of time. Then I think had a concern from this week. The last time we had the big box, so I think overall it's a win. But we're trying to balance all these things. So I could give that option as well, but we don't need a lot of work. We just want to give you a chance in case you made some, like, you added two numbers wrong together, right? So we don't need to see 10 different steps if you have a low box, just like a couple steps, and we can kind of know if you made like a numerical error. So yeah, so okay. So great. So I think that, oh, yep. Oh, so I mean, so far it was just like a one-line box. You couldn't hit return inside of it. So you could just, if the question was what's the expected value of x plus 3 and the expected value of x was 2, right? You could write this as expected value of x plus 3 is equal to expected value of x plus 3, and then 2 plus 3 equals 5, right? Just in one line. And I mean, we're not going to ask you to do any more complicated calculations than this. You can make them more complicated, but there's always, on the quizzes, we're going to ask you things that it's pretty straightforward how to answer, and it shouldn't be complicated. So they should be something that can just write down in one line. Yes, okay, great. So let's get into the lecture. All right, so joint probabilities for discrete random variables. I wanted to kind of talk about a couple things first. One, I felt, and this comes up on the homework. I wanted to review the exponential distribution. So just a little bit. I felt like I didn't explain this so very well. The PDF of this is f of x equals gamma e to the negative gamma x. The CDF of this f of x equals 1 minus e to the negative, so gamma a. And then you would write this as a random variable from the exponential distribution, and it has this parameter, so lambda. And we had written up the formulas and talked a little bit about this and plotted these. What I felt I didn't explain very well was this parameter, which is equal to the rate. Okay, and this is kind of the rate of some event that's happening, like then the next time that we're going to measure a drop of rain at the airport, if this is like a random event. So that's probably not a great example. So something that, so the next time, so let's see. So I've got example in my notes from, so there's like, some like nuclear processes where there's like these ionizing particles, and you have something that's running, and every so often there's like a particle that's ionized, right? And this happens at about, so according to this rate, and so it has like units, so it has like this rate is like the example would be like the number of times per let me, instead of times, let me say the number of events per second, right? So if I expect to have so it's kind of like so so if I'm expect this happens, so once per second, then it would be 1 per second, but that would be so this would be equivalent. So like 1 per so like 1 per second is going to be the so like the same thing as 60 per minute. So it depends on the unit here, right? So if I'm measuring in larger amounts of units, right, then I'm going to have more events happen in that span of time, right? So like it depends on the units, and so there's something about the exponential distribution is you can envision it as a continuous version of the geometric distribution. And remember the geometric distribution. So the geometric distribution was a discrete distribution. And so this was instead had a parameter p, and this is the probability that an event happens in the, like in the next discrete chunk. Okay, so the exponential is like if those discrete chunks are becoming smaller and smaller, then eventually they kind of blur together. So if you write that if you write the probability, so if I have so if I have my discrete so chunks, so if I have like n discrete chunks, so that I'm thinking about, then I can say the probability that so for this geometric distribution, that it does not happen, that the event does not happen in n discrete chunks, is 1 minus p to the power n. Yeah, so this n parameter, put this in here, right? So the probability does not happen after n discrete chunks. It's probably p it does happen. So if it doesn't happen for n of these time steps, it's 1 minus p to the power n. Yep. Each one is like a Bernoulli trial, yeah, and this is the event that, so the geometric distribution is like when is when the first thing happens, or when how many failures of this Bernoulli trial do I get in a row, right? Probably p is success, probably 1 minus p of failure. They're all going to be so independent of each other. So I can multiply the probabilities together and I raise it to the power n. Okay, so now I can think of what happens when I set p equals to gamma times t over n. All right, so this is useful when trying to calculate the probability of x so greater than t. So the probability that the geometric random variable is greater than t. So it happens so it's sometime so past t, so after t steps, and so what I can say is if I set p equals so gamma t over n, that's saying that every, so time, so t, and if this event is happening, so at a rate of like expect rate of like 1 time per second, but there are t of the seconds, then I'm saying this is the probability it's happening. So like each of the seconds, right? I can write this probability here as 1 minus gamma t over n to the power n. And so this distribution, or this thing, as I take the limit as n goes to infinity. So if I make the chunk size, I keep the rate of things happening kind of roughly the same, but I'm making the size of the chunk smaller and smaller. Then what's happening is this converges to e to the negative, so lambda t, and this is 1 minus the CDF of t for the exponential distribution, right? So I'm doing 1 minus 1 minus, and I get back the e to the minus, so gamma t. So as I'm making the resolution of my chunk getting smaller and smaller, this is kind of thinking of like I'm taking an integral of a continuous distribution, but I'm doing it at discrete intervals of smaller and smaller chunks. Then, so this is converging to the exponential distribution. Yep. Yeah. So again, this goes back to this variation of there are these two different versions of the geometric distribution. One is where I'm counting the number of failures until I get a success, and the other is the number of trials until that last one is the success. What's happening here, and I could be adding, right? I could think of adding this probably p here at the end, okay? But what's going to happen is n gets very large. So let's see. So I'm what's going to happen to this p is n gets very large. This should get a very small probability of it actually happening the last chunk. So that makes as n gets very large, what's happening is it's approaching the continuous distribution, and the probability of it happening exactly at that point goes to 0. And this way of thinking about it doesn't make as much sense anymore. So instead, it's easier to talk about the version where we're just looking at the number of failures instead of the number of trials until the first success. Yeah. So I still have that. So P on front there. Yeah. Right. So let's see here. What am I doing here? So let's see. The difference is, yeah, this is a good question. The difference is I'm looking at the probability x is greater than t. Okay, so instead of so I'm not exactly doing the PDF here. So I'm just taking this part and bringing this down. If I look at the probability x is greater than t, this is equal to the sum of, let's see, t equals, of t equals, or let's say of j equals t up to infinity of 1 minus p to the t times 1 minus p to the power j times p here. That's a little bit hard to read. Okay, but so I can factor out this first term here. So that should be 1 minus p to the t times sum of j equals 1 up to infinity of 1 minus p to the j to the power p. Okay, and I'm going to argue that these things are going to add up to, this is exactly the, so yeah, what's going on here? This is exactly the, all the possible events of, the PDF of the, geometric distribution, right? So this looks again like the geometric distribution. This part happens after the t step. So all of these terms, because it's a PDF, all these should add up to 1. Okay, so I can factor this out as a 1, and all that's left is this term in front here. Okay, so yeah, okay, so that was a missing step in my note, but I think we solved it on the fly. Yeah, so, okay, so the geometric distribution has this effect that it's like memoryless, which means that after an event has happened or after a period of time, what the rest of the time looks like is independent of what happened in the past. And so that's kind of it's kind of what's happened here. So all the events after time t, the probability that you had only failures up to time t. So that's why you get this green box here that gets it can be factored down into that black equation. Okay. All right, so I just kind of wanted to talk a little bit, think about this rate parameter, the units of this matter. So as you shrink them down, eventually it becomes a kind of, you have to pay attention to the units as your time shrinks, then the rate has to kind of change with that factor. And then in the limit, it approaches the exponential distribution. Okay. Great. I just wanted to review that. Let me say one other thing that we didn't get to, which is important. We will talk about this again in the statistics part of the class. So the quantiles. So the quantiles are another aspect of a probability distribution. So if I have let's say a random variable from some form of distribution, and I have the CDF of this distribution, right? I can think of drawing the CDF like this, where I have some some real values, and it goes from 0 to 1, and this will be f of x, and it's going to be monotonically non-decreasing. Okay, and at some point okay, it's going to reach a level, it's going to hit 1, and it's going to stay at 1 afterwards. Okay, and what the quantiles are, if I take values along this y-axis, okay, and I draw them over, and I come down, this value here, quantile, this is the 0.5 quantile. Okay, so this is the, so the so formally the pth so quantile, and so this would be the, so 0.5 quantile is the smallest, so number, QP, that's what this is, this would be Q, so 0.5 here, the smallest number QP, such that F of QP equals the probability that X is less than QP equals this, so this value P. Okay, so all right, so it's a way of mapping from the y-axis, which are values 0, 1, down to the x-axis through the CDF. All right, so was someone know another name for the 0.5 quantile? What would be another name for a 0.5 quantile? So not the mean. The mean is like the expected value of the PDF, which is a similar concept. Yep. A percentile, yes, we think of them as like, it'd be like the 50th percentile. The 50th percentile might be, yeah, similar terminology. Yeah, so this is a special one called the median. Okay, the median is the point of the distribution where half of the probability is on exactly either side. Okay, we'll talk about the median in statistics in so a few weeks. Right there, you think you actually have data, and then you have half your data points on either side. Okay, but now instead, I have half of my probability of a full distribution on either side. This is the median. But there are other interesting quantiles. You know, this is a general thing. You can often look at the 0.25 quantile, right? So this would be Q 0.25 or the 0.75, right? And so this would be Q 0.75, and then this region in between them, this would be called the so quartile, so range. This is the range evenly kind of in the middle of the distribution that contains 50% of the probability. Okay, between the 25th quantile and the 75th quantile. So this is kind of a useful measure of like the middle part of like the distribution. So okay, so this is kind of a useful kind of property to think about the distributions. That's a little bit different than what we talked about before. Yeah. Yeah, so when we get into the statistics part of it, the box and whisker plots are typically made over actual data as opposed to a probability distribution. But you can apply the same sort of concept on probability distributions to kind of reason about these, right? And so, you know, this is often looked at with like the normal distribution. You kind of see it's kind of symmetric. The mean and the median are the same thing at that point, and the quartiles kind of work their way out. It's like, okay, I want the range that has 90% of the probability, and I can mark that range. This is 50% of the probability, but I could say I want a range that's 95 or 95% of the probability. Okay, so we will see these concepts more in the statistics part. So I just want to mention them here, that they work for the probability distributions in general, but these we'll revisit them. So this is kind of a first look at this. So okay, great. All right. So those are a couple things I wanted to catch up on. Let's finally get to what we're supposed to talk about. The joint, so probability for so discrete, so random variables. All right, so we've talked about kind of when you have multiple types of events, and we wanted to kind of look at, like, if you had these like sequential events, like I had two urns and they both had balls in them. Said with the probability, I picked the first urn and then I picked a red ball, and these were related to each other. They were events we're talking about, but a lot of probability theory and how it's discussed in the context of data analysis often is through random variables. And so there's a little bit more kind of rich way of talking about this with random variables. And so we're going to kind of more quickly work through a lot of the same ways of thinking about them, but it's sometimes a little bit more complicated to deal with. So random variables and the properties are kind of stronger with random variables. So we'll kind of, so see what's going on here. Okay, so the first concept is a joint, so probability, so density function. But this is going to be for two so random, so variables, x and so y. We saw this before, even just early in this lecture, with the single random variable x. But now if we have two random variables, we want to know how do these interact with each other. We want to talk about things like the joint probability, like the associated with these, the joint probability density function, the conditional probability, something called marginal probability, and then are these two random variables independent of each other? We talked about most of these concepts with events, but we're going to talk about them with these random variables instead. The key way to map this back is to remember we had this notation, which I think I introduced, which is when we have discrete random variables, we can think about this again through the sample space and the events in the sample space. So I could say this is the like event that x equals a, right? So then my random variable, again, it's like a discrete random variable. So there's certain events in a finite sample space where that random variable equals the value a. There was a question on the homework where you had a random variable x and you had to convert it to a random variable y, and you had both, say, -2 and 2. If I squared that value x, they could both wind up with another random variable y having the value 4. Okay, so there could be multiple ways to get x equal to a, but this is the event that x winds up as the value a. Let's say I roll 2 dice and I want to look at the sum of the values, and that's 8. Okay, maybe x is the sum of 2 dice. There are a bunch of things in the sample space where the sum of those values so could be 8, and this can describe a set, right? So we'll often talk about this will be one event, and then maybe I'll have another event with a different random variable that's going to equal so a value b. Okay, and so we're going to start with this. So then we're going to talk about the probability of these events, right? So this is, I can say the probability of x equal to A intersection the event Y is equal to B, right? This is something we've talked about, the probability of two events, the intersection of these two events. This notation, though, is, as many of you, not many, a few of you complained early in the class, this set notation is, so kind of clunky. So what's typical is to write this in a in kind of a simpler way. So instead, we'll write the probability that X equals to A, comma, Y equals to B. Okay, so this implies the same thing here. This is just a simpler notation, which is the convention. And then we will write this as a probability density function as well. We'll say there's a probability density function now on two random variables, X and Y, and it will take on values A and B. Okay, so now my PDF is a bivariate function. It takes in two values. Okay, so this will be our notation for the probability density function, the joint probability density function over the random variables X and Y. Okay, not too much harder. We just have two random variables instead of one random variable. And when you take, if you take the CS3190, the data analysis course, you'll maybe see this over a vector of values instead of just two values, A and B. And stuff pretty much works the same way. Once you get two random variables, it kind of works the same way with more random variables. Okay, and so this is the notation for the PDF. Okay, so what properties do we have? So we have two random variables, X, Y. We have the PDF defined F of X, Y, A, comma, B is equal to the probability that X is equal to A, Y is equal to B. Okay, so what properties do we have about this? Well, it's a probability. So we have that F of X, Y for A, B must be in between 0 and 1 for all A and B. So for all possible values A and B, I can put in that function for discrete random variables has to be between 0 and 1. We'll kind of do this somewhat all over again with continuous random variables. Then it's only greater than 0, but it has to be between 0 and 1 because it's a probability. Okay, and we also know that this is one property. The other property is that if we look at all possible outcomes, these have to add up to 1. So so if I look at F of X comma Y over AI Bj, and I sum this over all possible outcomes, then this has to equal to 1. So exactly. Okay, so they have to, all the possible events, the probabilities of them, if they're, this is where for all, so outcomes AI Bj, where AI is not equal to AI prime and Bj not equal to Bj prime, right? So these are kind of, think of each of these with different indices are going to be distinct. Be clear, the prime is on the J on the index there. So for different indices, those are different outcomes, and so they have to be distinct. So that means I can decompose the probability, and if I cover all outcomes, it has to add up to 1. Okay, this is the property of, like a PDF. So if I sum over all outcomes, now I have to sum over A and B. So not just the choices of A or not just choices of B. Yeah. Yeah, so you could think of having, having like nested for loops, right? So think of this, if this gets these tables, so we're going to start writing down some tables of these things through examples. The tables get very big and you have more and more random variables. This becomes not very efficient. So this is kind of a major problem within a lot of computational Bayesian statistics. You want to kind of figure out, you often get the function f, but you get access to a function like f, so called the likelihood, that you don't know how to normalize. You know things are proportional to that value and they add up to some constant, but you don't know what that constant is and you need to divide through by the constant so it becomes 1. But summing over all possible things becomes like, computationally too painful. So you often try to work around this in some way. Yeah, so typically you do 2 nested for loops, but if this got complicated, you could imagine 2 nested for loops or lots of nested for loops is not a good thing to do inside of an algorithm. It can become very slow very quickly. Right, but yeah, that's the right way to think about it. 2 sums, 2 nested for loops. Great. All right, so let's do a simple example here. Okay, and this is an example from from signal processing. Okay, so let's say some wire here, and so people are talking on the telephone, so across this wire. Okay, and this is so in particular how this works is I'm be sending bits across a channel. I can either send a 1 bit or a 0 bit across the channel. This is the sender, and the data goes across the channel. And on the other side, there's a receiver, and the receiver either gets a 0, either like a 0 or 1. Okay, but there's some noise across the channel, right? In computer science, we think about these channels as always being so perfect. If you send a 1 bit, it's going to be a 1 bit on the other side. And electrical engineering, you probably don't necessarily think that way. You think there could be a chance that it's corrupted along the way. And thanks to all of you, us computer scientists can pretend that it's not corrupted. That's a oversimplification of the fields. But so we can view this as now, given think of the S and R as these random variables that can take on values 0 and 1. Okay, so if we have a table here, we can think of a probability table, and I think I drew some examples of stuff like this before. But you have a sender that can either send a 0 or a 1, and a receiver that can receive a 0 or 1. Okay, and then there are probabilities of these events. You often see it like 0.45. So what this represents here, this value inside here, is the probability the sender puts in a 0 and the receiver is going to output a 0, right? Is going to receive a 0. Okay, so that both of those things happen. Sender puts in a 0 and receiver outputs a 0. Okay, so this will make maybe more sense once you see the whole table. 0.06, 0.41. Okay, so now I have probabilities of all the possible events, right? The random variables can take on these binary values, each 0, 1, and each pair of binary values, right? So I can write down something like, now f of s comma r takes on 0, 0. Was this value going to be? Yeah, this is exactly that first example. This is 0.45. This is the probability the sender gets 0. That's the first argument of the function, and the probability that the receiver also gets a 0, which is this second argument. Okay, so so that's how to read that. Okay. So this kind of, before we talked about a PDF for discrete random variables as thinking discrete possible outcomes we can write down as a table. Now with two joint probability between two random variables, we need to write this down as a two-dimensional table as well. Okay. Before we just had all the events and then and all the possible and the probabilities of all the events in another column. Now we need to really write this as a table. So all right, so something you can do here is you can kind of, one important thing to do off this table is to get what's called, the marginal, probabilities. I would like to use this table to get the marginal, probability, okay? And this would be something like probability f of s equals, 0, right? So the probability that the bit sent was a 0. I would like to get this from the table. How would I get this from the table? So I'd add a row, or I'd sum up along the row. Right, okay. Yeah, so I would look at the whole, let's say s equals 0, and I would sum up on this row. And what I'm going to do is I'm going to write in the, I'm going to write this in the margins. This is 0.53, which is 0.45 plus 0.08, right? This is called the marginal probability. And it's, you kind of write it in the margin of the table, and it's summing up along that row, right? So this is 0.53. And then I could also do this here. This would be 0.47, which is f of s equals to 1, right? That's summing along the row where s is equal to 1. I can get the marginal probability here. Okay. This is one important thing to realize about the marginal probability is now I've recovered the probability density function for f of s, right? This is equivalent to f of s. It's the probability density function, which means that if I add up all of the possible values of that, it should add up to 1. And indeed, this is the case. 0.53 plus 0.47 equals 1, right? So the total probability along the margin should be equal to 1. And it's true if I do it for the probability of r, right? So f of r equals of 0 is going to be 0.51, and f of r takes on the value 1 should be 0.49. And if I add these two things up, I'm also going to get 1. Okay, so if I add up along the margins, put the numbers in the margins, those should also add up to 1. Okay, so I can do this in either direction in the table. Okay, this seems pretty straightforward. So kind of just mathematically writing out the marginal probability. So I could say the probability of, say, x is equal to a. I can write this as the sum over j of the probability of x is equal to a times y is equal to bj, which is the sum over j of f of x, y, a, b, j. So all the way think about, so like marginalizing. If I marginalize a distribution, if you marginalize a population of people, you're kind of ignoring them. You're kind of saying, what would happen if I didn't consider them in the equation? Okay, and so that's what I'm doing. I'm marginalizing over b, or so over the values b over the random variable y, saying what happens if I didn't consider them, right? Well, then I just get a PDF having to do with x, right? So to get the PDF having to do with x, I marginalize out y. And I look at all possible values of y, and I kind of add those up, and I kind of combine those. And that's kind of, I can also see that as kind of pushing them into the margin of the column, or of the margin in the columns or of the rows, in order to do this as well. Okay. All right. Okay. All right. So let's do a quick exercise. Okay, I think we're doing good on time. Let's do a little exercise here, where we're going to have two. I'm going to have two fair coins. Okay, and I'm going to have the outcome. I'm going to have two random variables. Okay, and the first one is going to be h, is going to be the number of heads. Okay, so the sample space for h is going to be, or it's a random variable, but right, the sample space of this is 0, 0, 0, 1, or it's like heads, 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 tails, tails, heads, and tails, tails. I've used lowercase there because I use uppercase h as random variable, and h is the number of heads, right? So this can take on values on 0, 1, and 2. Okay, and I'm also going to have a value b, which is the binary number representing by the outcome. Okay, so this is the value in binary, where I'm going to assume that h maps to 1 and t maps to 0. Okay, so heads, 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 heads equals 0, heads, tails equals 1, is 0, 1, right? Heads, so tails, heads equals 2, and tails, tails equals 3, right? This is 0, 0, 0, 1, 1, 0, 1, 1. Okay. All right. So I want you as a class to kind of take a few minutes to write down the PDF of over these two random variables. All right, and you can drop people into some. Oh, you're not co-host. All right, why don't you go and work this out? Do you guys want to go in breakout rooms on Zoom? Go and talk with your neighbors. Try and write down this table. Yeah, most of you have paper out. Yeah. If h is great, I'm gonna swap this. So h is 0 and tails is 1. Great. So thank you. All right. Take a couple minutes. Try and write down what the PDF of this is. So, okay, do people still try to write this down, or? So do you want another minute to think about it? Or do you think you know how to do it and you just want me to work it out? Are you kind of confused what to do, or you're working through it? Yeah. So, okay, so let me start here. I'm going to start by writing down this table. Again, we're going to do this as a table, and we're going to have two random variables. We'll say H is on this side and B is on this side, right? And the values that H can take, I said, were 0, 1, and 2. And the values B can take were 0, 0, 0, 1, 1, 0, and 1, 1. Right, so I'm going to now put some lines in my table here. Okay, so these are the outcomes that can these values the random variables can take, right? So this is to describe the probability density function. I can describe it in a table. Okay, and now I need to write down the probability of each of these things, right? Okay, so what's the probability I got? Right, so is this what you had so far? You try something different? Okay. So what's the probability? Let's start with that I had 0, what's in this cell here? Okay, so I had 0, 0, and I had 0 heads. So heads corresponds with zeros, right? So if I had 0, 0, that means, so how many heads did I have? So I had 0 heads, right? So the probability that this event happened was 0. I can't have both of those things happen, right? In fact, the probability I had 0 heads, I had 1 head was also 0. And the probability I had exactly 2 heads, this was, and a 0, 0, this was 1/4. Right? Yeah. Well, so I said if I have 0, 0 corresponds with yeah, I had that before and I kind of was inconcise. So I changed that. Yeah, great. Okay, so that's part of it. Let's look at the other. Let's look at what if I had 0, 1, right? So I have this case here, heads, tails. How many? Can I have 0 heads? When I have a heads, tails? No, I have, this is probably 0, 2 heads is probably 0, and this happens 1/4. Right? I also get 1/4 here. This is a tails and then a head, so I get, again, 1 head. And then if I have 1, 1, I have 0 heads, 0, 0. Okay. All right, so this is so it's like a probability table. So I've, okay, and then I can marginalize this table, right? So if I want the probability of getting just the probability H equals to J equals to 0, this is 1/4. I'm just adding up everything in this row. If I add up along here equals 1, that's 1/4 plus 1/4 is 1/2, and equals 2 equals 1/4, just by marginalizing along here. All right, and I can also get the probability of each of the outcomes of the the binary values. So the probability of, right, so this gives me f of h along here in this table. To get f of b, I can write 0, 0. This is probability 1/4, 0, 1. Probability 1/4, 1, 0. Probability 1/4, and 1, 1. Probability 1/4. Right, so this, by marginalizing along the columns, I get f of b, that PDF. So, okay, great. So let me do one more concept for today, and then we'll wrap it up and do independence of discrete random variables on Thursday. So let's say, so conditional, so probability. Okay, so we want to do, so conditional probability. If you remember, we had probability of A given B. This is with events, was the probability of A intersection B divided by the probability of B. Right, so this was the definition with events. I would say condition on the event B, then I restrict my sample space to be B, and I divide through the probability I'm in there, and I look at the joint probability. Okay, well, we want to basically conditional probability with random variables. I can do this with the PDFs basically the same way. So I state probability that if I have two random variables now, x and y, then I can say probability x equal A given that y is equal to B, right? These are just, remember, that's my shorthand for the set. The event x is equal to A and the event y is equal to B. Well, this is equal to the probability of x is equal to A and y is equal to B divided by the probability that, so y is equal to B. Okay, right? That's just kind of using that kind of shorthand notation to define the events with the random variables. But what's nice is I can write this with the probability density functions as well, right? So I can say f of x comma y equals x takes on the value A and B divided by f of y is equal to B. This is equal, sometimes we'll write this as f of x given y of A, so B. Or actually what's more common is to, so is write the y is equal to B in the, so the subscript. Okay, and so this would be the definition of the conditional PDF of x condition on y is equal to B. Okay, so we can think of what we've done is we're in like a probability table, right? So we can think of being in one of these probability tables where x takes on A1, A2 up to AK, and y takes in value B1, B2 up to Bm. Okay, and now we're going to condition on y is equal to a certain, on say B2. So y is equal to B2. I need the marginal probability. I need f of y B2, right? I need to calculate this by adding up on that row. And so now I can have this row, I can say that f of x, y given B is equal to, where each of these entries here, this value here would be f of x y a ai b2, right? So that's the entry that was in the cell here. That was in the cell. And so now to get the marginal, or the conditional probability, I need f of x, y, ai, so b2 divided by f of y, so b2, right? So I get this one from down here and this one up here, and together they fill into this cell. So to get the conditional probability, I take that column in the probability table and I'm dividing through by the marginal probability of that column. I can do the same thing over the rows. It would work same way over the rows, right? Okay, so I can define this. I get a new probability density function, which is conditioned on one of the random variables taking on a, so like a certain value. Okay. Yeah. Yeah, right. So if I just wanted for a particular cell, like just the green cell there, I just want to compute this particular value, right? I would go and I would look up the value in the cell in the table, right? Which gives me the value here. And then I look up and I have the margin, right? Maybe I pre-compute all the margins, right? That seems like a useful thing to do. I have the margin and I divide through it. And the fraction of the joint probability over the marginal probability gives me the conditional probability. And so I can, to calculate those is the same way as calculating the individual events before. That's the same thing we did up here with the events appropriately defined. But now we can do this with the, with like these discrete, PDFs. All right, so I'm hoping this mostly seems pretty straightforward. The reason I'm kind of taking a lecture to define this stuff is that we're going to do the continuous joint, probably kind of the continuous joint random variables next, and we're going to have to kind of redo all this. But instead of like sums and stuff, we're going to have like integrals. And that part is kind of a little bit less easy to kind of totally grasp all of it. So hopefully this part with the discrete random variables seems pretty clear and straightforward. But when we go to the continuous random variables, hopefully that will seem straightforward too, because we did this first with the discrete ones. If we had just jumped to that, it's probably going to be slightly confusing. All right, let me quickly do one fast example. Let's go back to our send receive bits. Receive, this was 1, 0, or no, I had that backwards, 0, 1, 0, 1. Let's see, I had 0.45. I think this was 0.06. This was 0.08, and that would make, what was 1, 1? This was 0.41. Okay, I want to compute now so let's compute the joint, the probability, the PDF for R, given that S is equal to 1. Okay, so this is going to be a table. Okay, it's going to take on values either 0 or 1, and I want the conditional probabilities. I need to marginalize. Need to marginalize over S, right? So I'm going to need to compute these marginal probabilities: 0.51, 0.49. Okay, so those are going to be needed. So for the marginal, and so now to get, and I only need this one, right? This is the marginal probability that S is equal to 1. Okay, so now I can compute the probability that R is equal to 1 is equal to 0, given that S is equal to 1. And that's going to be, let's see, this is 0.08, 0.08 divided by 0.49. And, right, that goes up here. And I can similarly do the probability that the received bit is a 1 is 0.41 divided by 0.49. So I get, again, this kind of this probability. Now it's a regular probability density function over one discrete random variable, but it's conditioned on S equals 1. Right? So again, if I add these two things up, if I add these up, I get 0.08 plus 0.41 over 0.49. And because that the denominator was a marginal probability, the sum of these is going to be exactly 1, right? So this will make sense. Right? So okay, so great. So hopefully, so it's fairly straightforward. We'll talk about independence of these, which will be a little bit trickier concept than with the events. And then we'll go on to continuous random variables and the joint probabilities. All right, so see you on Thursday. And the quiz will start at 5 p.m.
Thank you.